This lecture will look at voting schemes a little more closely, and the main message of this segment will be that even very reasonable sounding voting schemes can run into problems. And we'll do it by a series of examples. We'll look at situation. I'll ask you to pause the video and think about the situation, and then to continue when you're ready. So let's get started. Let's start with the Condorcet condition, which on the face of it is incontrovertible. And consider the following examples. So here we have 1,000 agents, and here are their preferences. So for example, 499 of them prefer A to B to C, and so on for the others. First question is, not every voting situation has a Condorcet winner. Does this one have? So it's a good time for you to pause the video and think about it. Well, the answer is yes. There is a Condorcet winner, and it's B. And why is that? Well, let's look at the relative preference of B to A and the relative preference of B to C. Well, we have here that 501 of the agents prefer B to A, and 502 of the agents prefer B to C. So clearly B is the Condorcet winner. Well, so where's the problem? Well, now think about the simplest sort of voting we're familiar with, plurality voting. Everybody votes for their top candidate. Who would win the plurality voting here? Well, again, you could pause the video, or in this case, it's fairly straightforward, right? Clearly, A would win it because 499 agents would vote for A, and the next highest number would be C with 498. So plurality voting doesn't give you the candidate that on the face of it is the should be the clear winner. What about voting plurality with elimination? So this might take a little more time to think about. So you might want to pause the video here just for a second. And now when you think about it, you see that C would be the winner under plurality with elimination. And why is that? Well, you'd first run a plurality, and you'll see that B is the loser, so B would leave the competition, if you wish, and now it'll be head-to-head between C and A, and in this case C would be the winner because 501 out of the 1,000 agents prefer C to A. So C would be the winner. And so two voting schemes, both of them on the face of it reasonable, would give you different answers, and both answers different from the criterion that on the face of it seems quite a safe criterion, namely the Condorcet condition. So here's another example, and let's think about what would happen in this case. What would happen under plurality voting? Well, clearly under plurality voting, A would win, since A would get 35 votes, and the second highest would be B with 33. What would happen under the board of voting? This takes a little more thinking, and you might want to pause just for a second the video. But when you continue, by that time you'll quickly realize that, again, A would be the winner under Borda. And clearly you have A, B, and C each appearing in each of the places 1, 2, and 3, with A appearing with the largest number of agents in the higher locations. So A would have the highest Borda count and would be the winner too. So this looks very good. But now what happens if C drops out? So C realizes that he has no chance of winning the election and drops out. Now what would happen under the both plurality and border? Just, you might want to pause for a second the video and think about it. And when you do, you realize that in both cases, B would win. And so here you have a candidate that has no chance of winning, and his sole role, if you wish, is to change what otherwise would be the outcome of the elections. Here is another peculiarity of voting schemes. And imagine that we're doing pairwise elimination. That is, we're going to take one candidate, compare him to another, take the winner, comparing to a third, and so on and so forth. So the order in which we compare the candidates, we call that the agenda. So somebody needs to set the agenda. We call that person the agenda setter. So imagine pairwise elimination with the order of comparison A, B, C. In other words, A will be compared to B, and then B will be compared to C. So who would be the winner of this election? A good time to pause the video and think about it. And once you do, you realize that C would be the winner, because when A is compared to B, well, we have B preferred to A by a majority of the agents, so A would be eliminated. And then when the winner, namely B, is compared to C, you'll see that C is preferred to B by the majority of the agent, and therefore C will be the winner of this election with this ordering. What happens with another ordering, like ACB? Again, you might want to pause the video, and by the time you resume, you'll realize that in this case B would be the winner. And perhaps not surprisingly, when you ask about the third ordering, BCA, you'll see that A would be the winner then. And so it's a little perhaps disconcerting that the same voting scheme, merely by deciding on the order in which you run it, will lead to very different results. And here is another example. There are 3 agents and 4 candidates, and the preferences are as written up there. Now, consider again pairwise elimination with the ABCD ordering. And what would you get? Again, pause the video for a second, think about it, and realize that the winner would be D. What about this case? We're now not talking about different orderings. We're talking about a given ordering and an outcome, but there's something a little troubling about this outcome. What is it? Pause the video, think about it, and realize that the problem is that everyone prefers B to D here, right? So B is preferred to D here, B is preferred to D here, and B is preferred to D here. And yet D, this Pareto-dominated candidate, wins. So something is wrong in this picture. Well, the goal here was not to give us the final answer what is the right way to vote. In fact, that is not well defined. The goal was to alert us to the fact that a lot of reasonable sounding voting schemes can be problematic. And so with this note of caution, we'll finish this segment.